Okay, welcome back. This is section 2.5. We're going to be talking about how to solve quadratics by factoring. So we're going to review some of the factoring techniques that you learned in Algebra 2 or Algebra 1. We are also going to utilize the zero product property that you learned in middle school, and we're going to utilize both of those techniques to solve real-world problems. So first, let's flash back to Algebra 1. One of the first things we learned was the distributive property, and then you learned that you could undo the distributive property, and that was called using the greatest common factor, and this will still always be the first thing you look for. So when we have a polynomial with more than one term, we are going to look to see if there is a common factor in all of the terms. And in this case, you can see that the a is a common term, and so we can factor out a, and we're left with b plus c. You also learned about perfect squares, and we reviewed this in the completing the square section. So don't forget that if you look for a trinomial that has a perfect square both first and last, you can check to see that the middle term is twice their square, the product of their square roots, and then we can factor that into a perfect square. We also have a difference of squares technique, so that if you have the difference, so that means you're subtracting two squares, we can rewrite that as a minus b times a plus b. And then a sum and difference of cubes. And a sum and difference of cubes may be new for some of you, and we're going to talk about that a little bit more when we talk about polynomials. But basically, if you have two cubes, so a cubed and b cubed, and you're either adding them or subtracting them, either way, you can factor them into a binomial and a trinomial. And the binomial will always have the same sign as the original expression. And so it will always have the same sign. And then in the trinomial, the first signs would always be a squared and then plus or minus, and it will always be the sign that is opposite from the original. And then it will always be AB, which is different from a perfect square. A perfect square is 2a. A sum and difference of cubes will always be AB, and then it will always be positive, so it will always be plus b squared. And so we can use SOAP to help remember which sign goes where in the sum and difference of cubes. So it's always the same, S, opposite sign, always positive. Okay. So if you need some extra help with simplifying polynomials or factoring and the different factoring techniques, please make sure you go to Khan Academy and have those mastered before you continue on with this video. So again, the first thing we're always going to look for is the greatest common factor, and we notice that each term has a factor of x. So we're going to go ahead and factor that out. So we end up with x squared plus 3x minus 54. And then we want to see this trinomial and see if that will factor. So we want to utilize our trinomial factoring techniques, which is what multiples of a, remember there's a 1 here, of AC, so negative 54, add to b, which is positive 3. And we know 9 and 6 are factors of 54. And in order for 54 to be negative, one of these has to be negative, but we want to add to a positive, so we're going to make the bigger number positive. And so positive 9 minus 6 is plus 3. So that means that this trinomial is going to factor to x plus 9 times x minus 6, and of course we still have the x in front, and there is our fully factored polynomial. We can also do this with things that may not look like a difference of squares, but upon second glance we notice x to the fourth can be rewritten as x squared squared, and 81 can be rewritten as 9 squared. And so now we have our a and b. And so we can use difference of squares to rewrite this as x squared plus 9 times x squared minus 9. And then, before we even finished, we noticed that x squared and 9 are also squares, and we're subtracting, so this is another difference of squares, so we can factor this one more time. So x squared plus 9 is still there, and that can't be factored. There's no such thing as a sum of squares. And then we have x plus 3 times x minus 3, and now we have a fully factored expression. Okay, so why do we do this? We do this because if you remember in middle school, we talked about the fact that if we multiply two numbers or expressions together and they equal 0, then one of those numbers or expressions has to be 0, because 0 times anything is 0. And we can utilize this when we factor polynomials. So if we know x squared plus 5x minus 14 equals 0, because remember, the 0 of a function is where it crosses the x-intercept, so that's where y equals 0. So if we started with y equals x squared plus 5x minus 14, and we want the solution or the root of that equation, we set y equal to 0, right? So we have this equation. We can factor this to x plus 7 times x minus 2 equals 0. And so if these multiplied together equal 0, then we can rewrite it as two separate equations, either x plus 7 equals 0 or x minus 2 equals 0. And if that's true, we can utilize our simple equation solving techniques that we learned in 6th grade. So x plus 7 equals 0, so if we subtract 7 from both sides, then we get x equals negative 7, and if we add 2 to both sides, then we get x equals 2. And so here are the solutions to the quadratic. So let's go ahead and try our factoring techniques to solve a quadratic. And when we look here, we notice immediately that there's an x in both terms. So we can factor out an x and we're left with x minus 4 equals 0. By the zero product property, we can then write x equals 0 or x minus 4 equals 0. Now this already gives us a solution, so x equals 0. Here we have to solve the equation, so if we add 4 to both sides, we end up with x equals 4. And so now we know that x equals 4 and x equals 0 are solutions to this quadratic equation. Okay, if we look at this question, we realize that x squared minus 5x plus 6 has no greatest common factor, so we need to utilize a different factoring technique. So if we look at a, which is here 1, times c, so positive 6, but adds to negative 5. And so we look at the factors of 6, 6 and 1, and 2 and 3. We know we need to multiply to a positive number, so they're either both negative or they're both positive. And regardless, this will always add to 7 or negative 7. And so if we look at 2 and 3, if we make them negative, we end up with negative 5. So that means we can factor this trinomial into x minus 2 times x minus 3 equals 0, which means that either x minus 2 equals 0 or x minus 3 equals 0. And using our inverse operations to solve the equation, x equals 2, or add 3 to both sides, x equals 3. Therefore, x equals 2 and x equals 3 are solutions to this quadratic. In this case, we notice that we don't start automatically with everything equal to 0, but that's okay. We can utilize our inverse operations to go ahead and subtract 3x from both sides. So now we can rewrite the equation as x squared minus 3x minus 18 equals 0. We check for greatest common factor and we notice that there is not one. So we're going to utilize our trinomial factoring technique. So what multiples of AC, so negative 18, add to negative 3. 6 and 3 have a difference of 3 and multiplied 18. We want them to add to negative 3, so negative 6 plus 3 will add to negative 3. So we can rewrite this as x minus 6 times x plus 3 equals 0. Utilizing the zero product property, we can rewrite this as x minus 6 equals 0 or x plus 3 equals 0. And utilizing our inverse operations, we can add 6 to both sides, so x equals 6, or subtracting 3 from both sides, x equals negative 3. So the solutions to our quadratic equation are x equals 6 and x equals negative 3. One more time, we notice again that we have to set everything equal to 0, so we're going to subtract 576 from both sides. So we end up with 16x squared minus 576 equals 0. We don't have any greatest common factor, nor do we have a trinomial, but we do have a difference. And so we check that 576 is indeed a square. It's 24 squared. So that means we can rewrite this equation as 4x quantity squared minus 24 squared equals 0. And so now 4x is our a and 24 is our b. So we can rewrite this as 4x plus 24 times 4x minus 24 equals 0. And so by the zero product property, we can rewrite this as two separate equations. 4x plus 24 equals 0, or 4x minus 24 equals 0. Now, if we utilize our inverse operations, so subtract 24 from both sides. So now 4x equals negative 24. Divide both sides by 4. And you end up with x equals negative 6. And on this side, we're going to add 24 to both sides. So 4x equals 24. Divide both sides by 4. And x equals 6. So the solutions to our quadratic are x equals 6 and x equals negative 6. So now that we know how to go forwards, so we can factor, rewrite it as two separate equations, and solve those simple equations to find our roots. We can also go backwards, and what that means is if we're given roots, then we can solve for 0 or rewrite them as two separate equations. If those two expressions equal 0, then the product of those expressions must also equal 0, and we can utilize our distributive property to rewrite it as x squared. X times negative 2 is negative 2x plus 7x is plus 5x minus 14 equals 0, and therefore there is a quadratic equation y equals x squared plus 5x minus 14 that has roots of negative 7 and 2. Now there are other quadratic equations that will have the same roots, and we will talk about that in class. Okay, so let's do an example. So if x equals 3 and x equals negative 4 are roots, then we can utilize our inverse operations, so subtract negative 3 on both sides or add 4 to both sides. And we end up with two expressions, so x minus 3 equals 0, or x plus 4 equals 0. This means we can write both of these as products, and they'll both equal 0. So x minus 3 times x plus 4 must also equal 0. And by the distributive property, x squared, 4x minus 3x is plus x, negative 3 times 4 is negative 12, must equal 0. Therefore, there is an equation where y equals x squared plus x minus 12, where the roots are 3 and negative 4. In addition to writing quadratic equations, we can also use quadratic equations to solve real-world problems. So let's say, for example, there's a rectangle. So we'll draw the rectangle, where the length is 2 feet more than its width. So that means if the width is w, the length is 2 more feet, so w plus 2. And the area is 63 square feet, so the area equals 63 square feet. And so I want to think, what relationship do I know between the area and the length and the width? And I know that area equals the length times the width. And since I know the formula, the value of the area, I know the area is 63. I knew the length can be represented by w plus 2, and I know the width can be represented as w. And now I have a quadratic equation that I can simplify and solve. So first I'm going to start by distributing. So w squared plus 2w equals 63. And then if I subtract 63 on both sides, I end up with 0 equals w squared plus 2w minus 63. I have no greatest common factor and I have a trinomial, so I'm going to utilize my trinomial factoring techniques to determine what multiplies to negative 63 but adds to 2. And I know that multiples of 63 include 9 and 7. And so if I want to add to a positive number, if I make 9 positive and 7 negative, That's going to add to 2, and positive 9 plus negative 7 is negative 63. And that means I can rewrite this quadratic as w plus 9 times w minus 7. By the zero product property now, if these multiply to 0, then w plus 9 must equal 0, or w minus 7 must equal 0. If I subtract 9 here, then w equals negative 9, or if I add 7 here, then w equals 7. Well, a width can't be negative, so this answer, negative 9, can't possibly be an answer. So we're left with w must equal 7. So if the width is 7, then the length must be 7 plus 2, which is 9. And 9 times 7 is 63. So that means that the width is 7 feet and the length is 9 feet. Okay, thank you so much for listening. If you'd like some more examples, please make sure to watch the More Examples video below. Otherwise, go ahead and complete the 9-2 solving quadratics by factoring reflection. And up next, we're going to learn about complex numbers.